All right, so we are going to start off with units, unit conversions, and density. I'm going to have to delay everything I say because the slides are delayed, but basically as an overview, and if you've had chemistry before, or if you've had Chem 20 especially, this should all be pretty much review. That being said, we're going to spend a couple lectures going over this stuff. Chem 1 really is a lot of Chem 20 over again, but to a deeper level. Oh, scientific notation. Before actually we even look at that, right? Because scientific notation is how we write really large numbers and really small numbers. And to just give you some context for that, this is where that music was coming from. Forgot that it had music. Okay, so what's the largest thing that somebody can think of? Blue whale. We can start with the blue whale and we move our way up because this has a lot. I'm sure they've got a blue whale in here. All right, so we're gonna go, oh, elephant, there's blue whale. And then I also heard galaxy. So we got the Eiffel Tower there. No, infinity's cheating. Infinity is almost more of a concept than a tangible thing. Okay, there's a neutron star. Look at that, neutron star is smaller than Rhode Island. I just think it's really funny that they included Rhode Island. It's random. Huh? Maybe. Possible. Or they're from Rwanda or West Virginia. Those are also in here. Anyways, going up, California. Now we've got some planets, moons really, and then planets. There's the Earth, Sirius B, which is a star that's nearby. A Minecraft world. Pretty big. Depends on your computer. There's the sun. There's a whole bunch more stars. It's basically, I think, stars from here on out. And they just keep getting bigger and bigger. And we haven't even gotten to a galaxy yet. The Kuiper Belt, not a galaxy. That's just like the asteroids and stuff that are like hanging out beyond Pluto, which Pluto, Kuiper Belt object. So still haven't gotten to the size of a galaxy. Oh, there's the Stingray Nebula, which would be one star that exploded. Blinking Nebula, Ring Nebula, Oort Cloud, Clone Nebula. Where's a galaxy? Omega Centauri, is that a galaxy or is it just... Yeah, so now we're starting to get some galaxies. Dwarf Galaxy. And we are in the Milky Way. And there's the Milky Way galaxy. Really big number. Sorry, you guys in the back. It's actually a small number for you guys in the back. Try to make it just a little bit bigger. This is why we need scientific notation, because this number is too long to write down practically anywhere. We'll talk about units too, which can be useful too, because a meter here is not a useful unit because it takes however many of these there are, a zettameter. Right, so 1 or 10 to the 21 meters. But now let's go the other way. What's the smallest thing somebody can think of? Aside from an atom. Oh, a quark. Okay, no, that's fine. We'll see other stuff on the way. I'm gonna go real fast now. Now we're back to human. So that's our scale. And as we zoom in, there's a coffee bean, glass marble, pencil lead, an ant. Width of a human hair, similar to a thickness of paper. Now we've got a cell nucleus, mitochondria, powerhouse of the cell. Got to say it every time. HIV, so smaller viruses, phospholipid. Now we're getting to individual molecules. And there's a hydrogen atom. So that's including the electrons around it. And if we get even smaller, there's a uranium nucleus, chlorine nucleus, helium, and then proton. And now we're down to 10 to the minus 15, right? And again, really small number, not practical to write down. This is why we have scientific notation. But heard quark, so let's see how small a quark is. It's the range of the weak force. Up quark and the down quark, the largest quarks. So quarks, if you didn't know, quarks are what make up atoms. Really, they make up the protons and neutrons, made up of different types of quarks, subatomic particles. That's too small. That's basically just physics. This is chemistry. So we'll be dealing with stuff larger than that. But this is an attometer, 10 to the negative 18. And so we've almost gotten, there's a neutrino, there's a zeptometer. So we went all the way up to 10 to the positive 21 meters, which is really big. This is 10 to the negative 21 meters. Now it's really small. And so scientific notation basically is the way that we take all of these extra zeros and we truncate them, we abbreviate them, and write them as that 10 raised to some power. I need to do that. So science is pushing the boundaries on both ends. Now in this class, we will deal with small amounts of things. When we talk about the number of atoms, we'll be talking about a large number of things. But that's what scientific notation is for, and that's what we use it for, is basically taking these huge numbers and making them easier to write down. So something like 10 to the 14 light years. Actually, is this going to work? It didn't work yesterday. I don't know why it works. It doesn't work. So something like 10 to the 14 light years. Or sorry, not 10 to the 14. 14 billion light years, right? Really big number. We could rewrite that as, does anybody know how we'd write that in scientific notation? So first thing we need to know is where's the decimal? It's implied here. Yeah, it's at the very end of the number. So it's there. And so we're basically taking that decimal, we need to move it over here to get a number that is between 1 and 10. So 1.4 is greater than 1, it's less than 10. And that means that we have to move it over 1, 2, 3. It's going to be slow. 4, 5, 6, 7, 8, 9, 10. And it's a large number, so it's 10 to the positive 10. And so that would be light years. Now this other number, is this a very large number or a very small number? Very small number, right? Negative exponent. So we raise it to the negative exponent. Basically means we're dividing by 10 times. Okay, so hopefully that was review. I think actually scientific notation is in the review part of ALEX. Oh, that was something I forgot to mention. The knowledge check on ALEX is going to ask you about things that you don't know about. And you should not take, I think actually one time when I used ALEX, somebody took 7 hours to do the knowledge check because they wanted to go through and get all the stuff right in the knowledge check. And I admire the dedication. That's not what the knowledge check is for. It's just probing at, what do you know right now that's going to be in this class, really? And you don't know everything that's in Chem 1. Maybe, I don't know, maybe some of you have done a lot of your own outside learning, but there's probably going to be a lot of stuff on there you don't know, and that's okay. Do your best, give it a try. There's an I don't know button for a reason. And then that will get you to the review module. And then in the review module, it's almost entirely math. There's a little bit about charges and how charges interact. So that shouldn't take you, I think that Alex's estimate was like an hour, even though it's like 21 different things. Some of it's just like, how do you multiply? How do you divide? All right. So here's a sad story of where units went wrong, right? Because we've talked about scientific notation, so we talk about really big things, really small things. Units are another way, actually, that we abbreviate really large numbers. So this Mars Climate Orbiter, they actually launched it in, I did more looking into this year, they actually launched it in December of 1998. And the building of that Mars Climate Orbiter took place even a year or so before that. They like started building it and they worked on this thing. And then they finally launched it. And then it wasn't until September in 1999 that it actually got to Mars. And it was that point that the people who had been working on this, the dedicated years of their life to this project, found out that one of the computers had been built using English units. And another computer was built using metric units. They were all supposed to be metric. So when they sent some course correction information to the satellite, it didn't do it correctly. And I guess 2 years of work, crashed into Mars. And I think it ended up, yeah, 125 million. And really, it all came down to the fact that somebody used the wrong units. Now, I guess I've said in the past, most of you probably won't be using, in situations where units are going to matter this much, make the difference between $125 million, losing $125 million. But I thought about it more and I was like, maybe you will. I don't know. If one of you guys goes and works at NASA, that'd be super cool. If you are nursing, units could be a life or death difference depending on dosage. Yeah. Which, priceless, right? For everything else, there's MasterCard. Sorry. When I'm teaching classes later at night, the ADHD comes out more. So units are important. I just want to like try and ground that in this story that like it took 9.5 years, or 9.5 years, excuse me, 9.5 months of this climate orbiter just traveling from Earth to Mars. And there were people the entire time waiting on the science that this was going to produce. But because of a unit error, it cost the whole project. In this class, it'll only cost you like half a point, but some of you will really care about that half a point, and I don't want to take it away. So the two main units systems are the metric system and the English system, and really secretly, the United States uses the metric system for everything. Anyways, so metric system, the English system, we will be using the metric system. And scientists use the International System of Units, SI units, and that comes from this system, international units, it's French, and I don't speak French. These are critical because this could be the difference between 1 milliliter of a solution or 1 liter of a solution, or 1, I don't know, deciliter of solution. These, again, can have life or death consequences. The SI base units that we'll be looking at for the rest of the semester that you should remember, there's basically 1 unit for everything, every dimension that we can measure. So we have length. So how long is something? How wide is it? How tall is it? All length, all use the meter. And we'll talk about prefixes, and that's how you modify it. For mass, it's the kilogram. So it's actually not the gram, it's the kilogram technically. Recently, actually fairly recently, they changed the definition of the kilogram. Used to be that there was an iridium cylinder that they had, and actually they had several of them, so there were multiple kilograms, and they would keep it like in a vacuum, as pristine as possible. But even still, over time, it was losing mass. And the mass of the definition of the kilogram was changing. So they came up with a new way recently. So time is in seconds. That one's easy. We use that one. Temperature is in Kelvin, which is very closely related to degrees C. The amount of substance is actually the mole. So we're talking an amount of carbon. That'll be in moles. And then ones that we're really not going to use are like electric current, the ampere, or luminosity intensity, which is actually the candela. The ones that are going to be most important, though, are going to be meter, kilogram, second, Kelvin, and mole. And really the primary importance here is that whenever you read a problem, if it says even kilometers, you should hear the meter in that, and you should think that's a distance. If you see something that's written as grams, milligrams, kilograms, you should hear the gram part of that and think that's a mass, defining another way really to define an amount of something. So just to try and relate these, I think one of the difficulties of at least taking chemistry in the US is that because as a consumer of anything, it's always written in ounces, or it's written in pounds, or it's written in feet or miles. And so we don't have a really good grasp of what the metric units really mean. There's not an intuitive sense of how long a meter is. Actually, we could do this. Everybody just hold your hands up for how long you think a meter is. So here, come on, you guys in the front too. It should be something like this. But for some of us, yeah, it's like, I don't know what a meter is. How many is that? How does that compare to how tall somebody is? But if I say hold your hands up for what a foot is, well, I have some idea of what a foot is, right? So to try and help this, a meter is actually about the same as a yard. Foot is about 30 centimeters. 1 inch, this conversion will probably come up a lot, 2.54 centimeters. Time is it? 5:50. Oh, we gotta go a little faster. And also on here, 1 centimeter cubed is 1 milliliter. You don't really need to memorize like English to metric unit conversions. I care about those less. What you will need to learn are prefix multipliers. So prefix multipliers are basically how the SI unit system deals with the fact that a meter is this long. That doesn't work for how far is it from here to, I don't know, how far is it from the Pacific Ocean to the Atlantic Ocean, right? Talking about that in terms of meters, it's gonna be a lot of meters. So instead of having like feet or yards or miles, which are all completely different words, you use prefix multipliers. So to say something longer than 1 meter, we might say a kilometer. So it'd be 1,000 meters. And so these are what you'll need to actually know and be able to use. And they all work on powers of 10. So here's the chart, all the prefix multipliers. You can use the one from the book, or you can go and you can Google your own because they're all going to be exactly the same. And the great thing about this is it's the same prefix multipliers for every type or unit of measurement. So it doesn't matter if we're talking about, right, because this is just centi. This could be centimeters, could also be centiseconds, it could be centiseconds, or it could be centiliters, or it could be centigrams, or kilos really gets used for more, right? Kiloliters, kilograms, kilometers, which is a kilometer, all the same prefixes. And I'll just highlight for you the most common ones. Kilo, centi, milli, and micro. There we go, there's the highlighter. And if you're a big old nerd like me, then you could remember these because it's the same as units of storage for computers, or at least approximately. So a megabyte is 1,000,000 bytes. A gigabyte is 1,000,000,000 bytes. A terabyte is another 1,000 times larger than that. Okay, now finally something that you get to do. There it is. How long is 4.5 capital M, lowercase m? I'm going to tell you what it is. In meters. So I'll go back up to this. So we want 4.5 capital M, lowercase m. Sorry, this is like really small for you guys in the back. A little bit larger. So really there's just one thing we need to know. What is capital M? Mega. So mega is 1,000,000. The mega millions. So 4.5 megameters is how many meters? Yeah, and you can actually, these are one of the ways that you can think about this. If you write 4.5 and I write mega, at least for words that places where we have words for them, megameters, you can basically take this mega and replace it with million. 4.5 this works better for things that are larger. There it is. Right, so this means 1,000,000. And we could rewrite 4.5 million. Right? I know how many zeros, or you should know how many zeros there are in 1,000,000. So 4, 5, that's slow. Okay, so 4.5 million meters. And we do this a little bit more mathematically. And this is what we're going to do a lot of. So 4.5 megameters I would fix the bug issue, but it requires that I restart my computer. Okay, if you've taken my Chem 20, you know that for the prefix version of this, we want to always make that 1 because we need a ratio here. We need a way to compare meters to megameters. So I want to put in here 1 megameter. How many meters are in a megameter? 1 million. Two ways we're going to write that. That's 1 million meters. Or in scientific notation, 1 times 10 to the 6 meters. Oh, wow. Can I make... Try doing this. Okay, is this coming back to some of you? I'm going slower than I said I would. Is it really warm in here? Is it just... Okay, for some people. For me, it's very warm. Okay, so if I do this math, these cancel out, and it's going to give me basically what I wrote on the other slide. 4.5 millimeters. So we can cancel out units. And then we can do this the other way. So 7.13 times 10 to the negative 9 liters is equal to how many nanoliters? So it's the prefix for nano. Let's take a guess. Oh, okay, yeah. Times 10 to the negative 9 is a nanoliter. Okay, now it's working a little bit better. I was thinking just like N. Right? N is a nanoliter. But that is 1 times 10 to the negative 9. So I'll write it over here. 1 times 10 to the negative 9 liters is equal to 1 nanoliter. So if I want to convert this, 7.13 times 10 to the negative 9 liters, I want to cancel out liters. So I put my 1 times 10 to the negative 9 on the bottom, 1 nanoliter on top. 10 to the negative 9 divided by 10 to the negative 9. It's going to cancel. So it's going to be 1.73, sorry, 7.13 nanoliters. Okay. How's everybody feeling? Going all right? Going okay? Getting sleepy? Getting bored? All right. So those are our basic unit conversions. Again, like I said, we're going to go through these pretty fast. One of the nice things about ALEKS is you can get as many practice problems as you want on these. Derived units work a little bit differently. This is actually a picture of my mom. Can you guess if she's Swedish or Japanese? She's Swedish. She actually went to the, just in case, I didn't want to throw anybody off. Hard to tell because it's whatever, not a great projector. Anyways, she's sitting there in a cubic meter. Showed it to a museum, I think it was in Norway, the Nobel Museum, and sat in that meter. Volume is a way that we measure the amount of space of something, and there's two ways that we can do that. One of them is with a derived unit, meaning meters cubed, centimeters cubed. And this is one of those things that, if you think about it, like, why do we call it cubed, right? It's a bad marker. It's called cubed because when you draw a cube, the volume of that cube is defined by 3 different lengths. And so if it's a perfect cube, and this is in centimeters, and this is in centimeters, and this is in centimeters, oh, I'm gonna test my drawing skills. Close. Centimeter times centimeter, so it's a centimeter cubed. It's called that because it literally defines the volume of a cube as long as all the sides are the same length. So that is a derived unit. We do have another unit for volume, though, the liter and the milliliter, which are not actually derived units, but they have equivalents to some derived units, like 1 centimeter cubed is equal to 1 milliliter. So other things, again, be miles per hour, meters per second, derived units. There's a lot of shenanigans you can get up to in physics with derived units, converting between things. Another way you can think about this is, right, how many small cubes measuring 1 centimeter on each side are needed to construct a large cube measuring 10 centimeters on a side? So how many cubes would I need to make up one side, or one part of this? Right, just 10. But then I also need another 10 to go back that way. And to make up the whole bottom of this, it would be 10 times 10. So it'd be 100. And then I need 10 of those layers tall. So it's 10 times 10. So you need 1,000 1 centimeter cubes. All right, density we'll spend a little bit more time on. The density of a substance is the ratio of its mass to its volume. It is a derived unit, yeah. And there's that density triangle thing that you can use to remember this. But you can also remember that density is because it's the relationship between a mass and a volume, it's a conversion factor in itself. So whenever you're trying to calculate the mass of something, and you know the volume, and you want to find, you know that you have the density and the volume, and you want to find the mass, you can just cancel units out to get the unit that you want. A lot of the time, it's going to be in units of grams per milliliter. Oh, hey, that kind of worked that time. Or grams per centimeter cubed. Density is a physical property that depends on temperature, and the dependence on temperature varies a lot. A lot of times, for the purposes of this class, we are going to assume that the density really doesn't change. But you can see that on this table, which comes out of the book, 20 degrees C is the density for all of these things. This is the density for each of these things at 20 degrees C. This is also an example of something called an intensive property. So intensive properties, they do not depend on the amount of substance. So if I have 1 milliliter of water, or if I have 1 liter of water, or if I have an Olympic swimming pool full of water, the density of water in each of those situations, assuming it's all pure water, is going to be the same. Doesn't matter how much I have. So it's an intensive property. I guess think of it as like intrinsic to that substance. And any amount of that substance will have that same property. Extensive properties are ones that do depend on the amount of substance. And this is one of those things that we're putting a name to a thing that's just no duh. The mass of water that I have depends on the amount of water that I have. Right, so if I have 1 milliliter of water, that's going to weigh less than 1 liter of water. And if I get an Olympic swimming pool of water, that's going to weigh even more. Do you have a question? No. So things like mass, length, volume, right? If I get more of something, it's going to take up more space. So those are extensive properties. Let's calculate then for this guy. A man receives a platinum ring from his fiancée, but before the wedding, he noticed that the ring feels a little light for its size. This is one of those things that's actually funny about density. You probably have some intuitive sense for what density is, because you look at something, you probably have done this with a can of soda, a can of something, and you go to pick it up and you think it's full, and then you pick it up way too fast because, oh, it's actually empty and you'd finished it. I guess that's a little bit different, but by looking at things, we make judgments about how heavy it's going to be based on what we expect it to feel like in terms of weight. So in lab, please remind me, in lab, we have a big old thing of mercury, sealed, so it won't hurt you, but it feels way heavier than it looks, which is a silly thing to say because we can't weigh things with our eyeballs. So anyways, this guy, he takes his ring, thinks it's a little bit light, decides to determine his density. Might be a chemist. So he places the ring on a balance and finds that it has a mass of 3.15 grams. He then finds that the ring displaces 0.233 centimeters cubed of water. So one way you could do this is you take like a graduated cylinder, fill it up to 5 milliliters, drop the ring in, the water level goes up. It's just like when you get into a bathtub, the water level rises because you're displacing water. So way easier than trying to figure out the geometry and calculate that for the ring. Okay, so remember that density is mass divided by volume. So 3.15 grams, is that a mass or a volume? Mass, right? Grams is a mass. So 3.15 grams. And then 0.233 centimeters cubed of water, is that a mass or a volume? Volume. I ask a lot of these questions, and you're going to think maybe that's a trick question. Usually it's not. So if I divide grams by centimeters cubed, what happens to those units? Huh? Yeah, it'll become grams per centimeter cubes. They don't go anywhere because they're different units. Now, there's a couple ways, and I feel like some people get confused when this happens. There's a couple different ways we can write the result of that. So 3.15 divided by 0.233. 13 point, we haven't gotten to sig figs yet. I'm just going to cut it off here. So a couple ways that we can write this with the units. 13.519, we can either write this as grams per, oops, I almost wrote milliliter, centimeter cubed, or we can write it as, these mean exactly the same thing, 13.519 grams per 1 centimeter cubed. So if I took this ring and whatever material it's made out of, right now I have less than 1 centimeter cubed. But if I had that material and I had 1 centimeter cubed of it, it should weigh 13.519 grams. It's working the same way here as miles per hour. Right? So if you drive 60 miles in 1 hour, your average speed was 60 miles per hour. If you drive for 3 hours then, drive 180 miles. Okay, so now we know the density. How do we know what the ring is made out of? Chart. Okay, platinum's down here at the very bottom. Sorry again, very small for you guys in the back. We might figure out a way, each of these actually has a computer in it. I wonder if we can get those to display back there because I'm doing everything on the projector. I'll look into it. Platinum should be 21.4 grams per centimeter cubed. Our ring is 13.5. Is it platinum? Definitely not. So to answer this question, not platinum, because this is an intrinsic property of platinum. Any amount of platinum is going to have a density of about 21.4, whatever it was, grams per centimeter cubed. This does not have that density, so it can't be platinum. Now, based on this chart, what does this chart seem to suggest that this ring is made out of? Mercury. What's the problem with that? Yeah. Supposedly the ring is solid and the mercury is a liquid at room temperature. So unless this guy is made out of ice, it's probably not mercury. It's probably some, we don't have all of the elements here. Could be something else. Probably not mercury, right? Okay, so let's, actually I think that's, oh no, okay, right? Okay, so we solved this guy's problem. And who knows where his wife got the ring, but she got scammed. So she takes it back though and returns it. She buys a new ring. Now this ring has a mass of 4.53 grams and a volume of 0.212 centimeters cubed. Is this ring platinum? So you've seen how to do this. Now go ahead and do it yourself. It's not to distract too many of you from it, but really, let's say this first. You should bring whatever calculator you're going to use for the exam. I got that basically the template for that syllabus was from somebody else. I actually don't care if you use a graphing calculator. I'm sorry if any of you went out and bought a different calculator because of that. So if you have one, you don't need to go out, and you haven't bought one yet, you don't need to go out and buy it, a new one. But you should be using whatever calculator that you're going to use on the exams. You should be bringing it to class. You should be doing all these calculations on it. You should be bringing it to lab and doing all the calculations there, because wouldn't it really suck to like not know how to use your calculator on the day of the exam because you were using your phone or you were using something else? I don't want that to happen to anybody. So try and get as much practice in it as you can. All right, so is this ring platinum? People nodding yes, yeah. And so we can get that again because density is going to be mass divided by volume. And usually that's going to be grams per centimeter cubed or grams per milliliter. It's a ratio though, so it could actually be any two mass and volume units. So 4.53 grams divided by 0.212 centimeters cubed is going to be 21.3679 grams per centimeter cubed. And that's pretty close to within margin of error of the density of platinum. Because realistically, how many sig figs do we have? I haven't talked about it yet, but 3. So our final answer should actually have 3. And if we do that, this 6 means that 3 rounds up and we'll get to 4 to nicely match the chart exactly. That doesn't always happen, as long as you're close, usually within 0.1. Okay, any questions about density? Nope, cool. I think actually we have one more question about density. So we said density depends on temperature. So which change occurs in a sample of copper when it is warmed from room temperature to 95 degrees Celsius? So we're told that the density of copper decreases as the temperature increases. So that means that as we take this copper, start at room temperature, which is lower than 95 degrees Celsius, because 95 is almost boiling. So we're increasing the temperature. So that means the density should decrease. And if we look at density as mass over volume, basically there's 2 ways that we can make density a smaller number. What's one of those ways? So one of them would be decreasing mass. So if my mass goes down, and what would be the other way? Increasing volume. Because if I make the number on the bottom larger, dividing by a larger number, that's going to give me a smaller number. Now, I have all the options here, right? Is the sample going to become heavier or lighter? Are we changing the amount of copper? It doesn't say that we're not, but we can assume probably that it's not just heating it up. It's not going to magically change the mass of copper. Those copper atoms aren't going to go somewhere. We're not going to get other copper atoms from somewhere. So it's probably the volume here that's changing. And in general, when you heat things up, they expand. So we have the same number of copper atoms, but because the volume increases when we heat it up, they're taking up more space. That decreases the density. The one, or I guess one of the times that's not the case is when you freeze water, making water colder. As it freezes, almost everything else becomes more dense and contracts. When water freezes, it expands, and that's why ice floats. because the density is lower than liquid water. Let's see, how much more did we get? Oh man. It looks like I went too slow. Okay. So scientific measurements. Basically, when in science, when you make a measurement and then you write that number down, how much precision you include, how many decimals you include, is important, because putting too many or too few, you're basically lying about your number. If I put more decimals down than my instrument was actually able to measure, then anybody else who reads that number in the future is going to think that number it's a better number than what I actually did. So scientific measurements, the general rule here is that every digit is certain except the last, which is estimated. So in these carbon monoxide concentrations over the years in Los Angeles County, they are certain that it was 9 parts per million, certain that it's 9, certain that it's 7, certain that it's 2, certain that it's 1, certain that it's 1. This 9, this 8, 4, this 9, point, right? This 0.0 even, those have uncertainty in them. And in this case, it's probably not that somebody read the instrument and the instrument was uncertain, but that they used a lot of different instruments and there's variance in all of those. Or there's a few instruments in there that are worse. And so that could be as high as 9.94, because that would round down to 9.9, or it could be as low as 9.85, because that would still round up. So this could be on the high end, a blob, 9.94, because that would round down to 9.9, 9.85, because that would still round up to 9.9. And so the uncertainty basically is in these numbers at the end is, does it round up, does it round down? Which is a lot more common with something like a digital scale. Basically, that's what we're going to be talking about here. And this is what you should remember. Scientists always read between the lines. For analog instruments, if you're reading a graduated cylinder, if you're reading a ruler, read between the lines. Whatever the smallest line is, you have to guess in between there. The number of digits recorded depends on the measuring device. On this scale, for example, measuring a pistachio, I'm going to zoom in on that. Each of these lines is representing 1 gram. And so that would be 1 gram. But we can see in these pixels that this marker here is slightly above that. And so we wouldn't just write 1 gram for whatever the weight of this pistachio is, because we can see that it's a little bit more. We wouldn't write 2 grams for this pistachio, because we know that it's less than that, it's in between. So how far in between would you say? Do you agree with 1.2? You think it's 0.2 higher than 1? Yeah? No? It's probably all right. So maybe think it's 1.3. I think this is a good picture for asking this question, because one, it's so blurry, but am I measuring from the bottom of the line? Because that'd be closer to 1.5. Or are you measuring from the top of the line? That could maybe be closer to 1.1. Or are we trying to measure somehow in the middle of the line? Usually the instrument will tell you where you're supposed to measure from. But in this case, because our smallest marker is 1, we measure to the 0.1 between those lines. We can't do any better than that. Good. I want to talk about meniscus. Now, for something like a thermometer here, right, we don't have this ambiguity of which side of that line do I measure from. The ambiguity is more in that their lines are so far apart. So that one's 100, this is 110. I guess we'll say degree C. What's the temperature how would you record the temperature there? 103, and actually let me do this. Is it exactly 103? So 103.1, 0.2, something in there, right? It's just a little bit past it. So we'd write this as 103.2 degrees C. But what if it was exactly on, make this a little more exactly on. And so what if it was exactly on the line? Yeah. We can't leave off that precision, right? We would say that's exactly on 105. If you leave it at 105, then the next person who reads this is going to assume that your thermometer was only good to every 10 degrees Celsius and that you estimated that it was 5 in between. And so we still include the 0 to say that this was good to 1 degree C, and I estimated that it was exactly on the 5. Last one we'll do, because I know we're out of time, just to look at this. Mostly you'll deal with this for the smaller graduated cylinders. This is called the meniscus, and it has to do with the surface tension. Basically, the water sticks to the glass. And not only does it stick to the glass, it'll climb up the glass a little bit on the edges. Now, what that means is this whole space inside of this contact lens looking thing is actually empty. So when we're measuring, and again, this should be review, we're measuring from the bottom of the meniscus, which would be about there. And these graduated cylinders are actually calibrated to take that into account. So they're actually less accurate if you're measuring something that doesn't have a meniscus. So what would this one be? Say 4.4? .5, yeah. Heard a bunch, 4.56, could probably be as high as 4.58, probably as low as 4.55. But that's why that last digit is an estimate. It's going to depend on how you read it. Now, the other thing that's not shown here is that when you're reading this, your eyeball needs to be level with the meniscus, the bottom of the meniscus. So when you're looking at this, if you're looking at it from too high up, you'll see, and actually you can see it here a little bit, at this 4 line, maybe I shouldn't use red. You can see there's a line there, and then there's this faint shadow around the back. That's the rest of that line as it continues around the graduated cylinder. And this is actually part of why, at least I think, that they're set up like this, is because here I can't see that line that would wrap around for the other side of 0.5. That means that this camera was level with 0.5. It's above the 4 line, 4.0, because you can see that line on the back. So that's one way you can use to tell if you're actually level, because that can change your measurement a lot. Okay,